Hello everyone, my name is Maxime Lucas on behalf of EFP Energie Nouvelles, where I work as a research engineer in environmental impact assessment. So EFP Energie Nouvelles is a French public research organization that has been a partner of the project since the beginning a few years ago. And now this project will finish next month. The aim of this project was to develop new technologies for CO2 photoconversion to produce high-value chemicals. And IFP Energie Nouvelles was responsible for assessing the new technologies, so their environmental impacts, but also their economic impacts. So we are not the partners responsible for the design and technology development, but only the assessment. So first, a few words about the project, that the technologies that we will assess in this project. Then I will introduce you to the main assumptions and the system boundaries that we will consider for our assessments. The environmental assessment first of the two technologies that we will develop, the photocatalyst reactor, PC, and the photoelectrocatalyst reactor, PEC. So the idea behind the SUN2CHEM technologies is very complex, yet it's very simple in a way that it mimics the natural photosynthesis cycle. So similarly to natural photosynthesis that you all know, we will use the CO2, the sunlight, and the water to produce carbonated chains, sugar chains. Here in the SUN2CHEM project, we will use not atmospheric CO2, but captured CO2 that we will try to convert into the chemicals we target. Here it's ethylene, so C2H4. So we may find some other impurities like hydrogen or methane, but these are not the molecules we are aiming for. So they will not be considered in these assessments, even though we can imagine that it brings an additional benefits to the overall assessment of the devices. So in this project, we assessed two technologies, as I said, the photoelectrochemical one and the photocatalytic one. So the first one is the photoelectrochemical device, PEC, that is developed by EPFL. And as I said, it will mimic the natural photosynthesis by mimicking the three steps, which are the light energy absorption. We'll have some electrodes, photoelectrodes, photoanode bismuth vanadate, and a photocathode in cuprous oxide here, which will create electric charges, electrons and holes within the material. Then the challenge is to separate these charges and ensure that they do not recombine directly into the layers, different layers, and that they migrate efficiently to the surface of the photocatalyst, where we will have the surface reduction of the CO2 into our desired product. So this is very challenging to target the ethylene product. And that needs to have a super fine engineering of the whole layer of the photocathode. So you see there are many layers here. This is an example, but in our project, we will assess these two configurations that you can see. So super exotic materials, layers of materials that we cannot find easily in life cycle assessment database. But we need to assess these whole combinations of metal layers. So you can see from left to right the bismuth vanadate anode separated by a Nafion proton exchange member. And on the right, the perovskite material in red and the silicium layer in blue with the charge collector on the right. So the light will come from the left and go to the right. So this is the first configuration that we will look at. The other one is the organic photovoltaic cell, tandem cells, where we replace this silicium layer with an organic material here. And we will assess the two configurations. So this was for the PEC device. Now we will look at another technology, as I said, the one developed by CNRS, which is apparently much simpler in terms of quantities and different materials used. We'll have the gas inlet, the CO2 from left to right to produce ethylene, with the light coming from the top, and a layer of catalyst in between different glass layers. So this calls for a very fine engineering of the heterojunctions, plasmonics, and metal organic frameworks composites. But it's much simpler since we don't have directly the photoelectrodes like the PEC device. So when we look at these two promising technologies, we can ask ourselves, what is the impact of the ethylene produced from these two devices as compared to the fossil one, the fossil ethylene? So this is the main question. Now we can also wonder, where are the impacts? What are the contributors to which impacts? So I'm speaking not only about CO2 emissions, but all kinds of environmental impacts that we will assess. And finally, we can ask ourselves, since these are very low TRL technologies, about 3 or 4, what will be the impacts once the technology has matured and that we increase the production scale of this technology and maybe the efficiency? What will be the impact of these technologies? So for that, we use a very recognized method for environmental assessment, which is the life cycle assessment methodology. It's framed by international standards, ISO 40 and 4040 and 4044. So we will assess our product from the production, from the raw material extraction, to the use phase, including the replacing of, for example, the photocatalyst that needs to be replaced over the project duration. But we will not consider the end of life, since we don't have much data on this, and it will bring more uncertainties than insights. We make a few assumptions that the devices are produced in France. The CO2 is captured in France from a concentrated mix of CO2 source, and that we don't have transportation of CO2 in between the plants. So regarding the production calculation of the ethylene, we used a few assumptions. The first one being that the whole CO2 captured react and is reduced to produce 1 kilogram of ethylene. We make some assumption on the conversion efficiency, which is 3% of the light. Energy from the light is converted into ethylene. And that brings us to the result that to produce 1 kilogram of ethylene from our photoconversion devices, we need 640 meters square of surface to capture the sunlight. So it's huge, and that you will see it has impacts on the results later. And we also make the assumption that our project is a 20-year project, and we make two different scenarios, what we call the lab scale scenario, where we have a 3% conversion efficiency, which is already quite optimistic assumption. And the energy for the manufacturing of our devices are the energy for the lab scale production, and the catalyst lasts 5 years. For the upscale version, we go up to 5% conversion efficiency, and we make the assumption that 90% of the energy will be saved from the manufacturing. Since the production efficiency of the device will increase, we will need less energy. That's our assumption. And the catalyst lifetime will increase to 10 years. So basically, in our comparison, we compare a reference system on the left, which we have our CO2 emitter, for example, a refinery that produces a product and emits a quantity of CO2. And we have also separately conventional ethylene production, which is based mostly on fossil fuel, on natural gas, to produce 1 kilogram of ethylene. This we will compare with our CCU chain, carbon capture use chain, where we'll still have our emitter that will produce the same amount of product, but this time one share that we called X of the CO2 emitted will go into our CCU chain and be used to produce our ethylene. So of course, we integrate the emissions associated with the energy for the capture of the CO2 and the conditioning of the CO2. But with substitution of our comparison, what's the same on the left and the right side, we can in fact not consider the output manufacturer, the CO2 emitter, since they are the same on both sides, but it will remain only the negative share of the CO2 captured. So the credit for the CO2 that will otherwise not be captured and be emitted in the atmosphere. That's the boundaries of our comparison. That will compare to, again, the conventional ethylene production on the left. So now moving to the results, the photocatalyst results first. So here you can see the results for the production of 1 kilogram of conventional ethylene on the top and ethylene produced via photocatalyst on the bottom. You can see also the range of environmental categories that we will look at for the example, the climate change, which are the CO2 equivalent emissions from the land use, the material use, the water use. These are all the categories. And in this graph, the darker it is, the worse it has in impact. So the darker it is, the worse between the conventional and the CCU chain. So you can see that the CCU chain has more impact, which is darker, in almost all environmental categories, except for the climate change categories, since we have credits for the CO2 capture. So what's interesting to look at are the climate change categories, of course, but also the energy resource, the use of fossil resource for the production. So for the conventional, we use fossil resources, which are natural gas. But what's interesting to see is that we even use more fossil energy for the production of our PC, our photocatalyst ethylene. We will see after why. Second interesting category is the land use. We can see here we use 0.13 as compared to almost 4 million points of land use because we need, as I said, 600 meters square of panel to convert the same equivalent of ethylene than with the photocatalytic reactor. So much more land use is needed. And also the metals and minerals category is important because we will use, you will see a lot more metal for the production of our CCU ethylene. So now that we saw the big picture of the results, we can ask ourselves where do the contributions come from which components of our systems. So that's what we're going to see here. You can see all the components, so the catalyst, the palladium catalyst, the steel from our reactor, the water, the glass, the CO2, meaning the energy for the capture of the CO2, but also the credit here that we have because we captured some CO2. All of these categories will be summed into the total for the photocatalytic ethylene and compared with the black one, which is the fossil ethylene. So for climate change, we see that we have a big credit for the CO2 capture, which brings us to negative values for the ethylene production as compared to the fossil. And for the energy resource, so here, as I told you that we use some fossil resources, it's because of the photocatalyst production that mainly depends on electricity, we will see later. And that we use a lot of metals as well for the photocatalyst and of water. So in all the categories, almost except for climate change, the photocatalyst is the main contributor. So let's zoom onto this photocatalyst, and we see that obviously the palladium in pink is the one that has a big contribution in all impact categories, but also in yellow, the electricity for the production of our catalyst. So we do the same calculation, but this time for the upscale version, so where we reduce the energy for the manufacturing, so we will use less electricity. And this time we see that the photocatalyst has much less impact in some categories like the resource use. So the fossil use came from the electricity used for the production of the photocatalyst. We still use a lot of metals compared to the fossil ethylene, but this is due to the palladium. So that was for the photocatalyst reactor. Now let's move to the photoelectrochemical reactor. So we have the same type of graphic, but here you see that even with the lab scale, upscale, version of the PEC, so 5% and 90% energy saving, we still we still have more impact, environmental impact in all categories than the conventional one, even in the climate change categories. So that means that even when reducing 90% of the energy for the manufacturing, we are still more emittive than the conventional one. And this is mostly due to the perovskite silicium tandem cell that we can see here. And even the CO2 credit does not enable to reach comparative GHG emissions as the conventional ethylene one. And this is the same for all the environmental categories that we look at. You always see the PSC, the perovskite silicium bar, that is the most contributor part. So we're going to zoom into this silicium tandem cell to see where are the contributions. And again, they are at the pink one, the energy for the production. And the other one is the perovskite material, the green one. So we can zoom into the perovskite, the green one, to see where are the contribution. And we see that they are mostly attributed to the components which are dimethyl sulfoxide, the lead iodide, the DMF, dimethyl formide, and lead bromure and cesium iodide. But what's to keep in mind is that even when reducing 90% of the energy for the production, it's still overwhelming in all impact categories. So that means that either our assumptions are not realistic enough, that we can save more energy for the production at a later stage, or that this perovskite solar cell use too much energy for production to be competitive with the conventional ethylene one. So moving a few parameters to see where we could increase our GHG scores. So we moved a few parameters. The first one is the lifetime of the reactor in year. So in y-axis, we have the emissions of CO2 per kilogram of ethylene. And we see that we need to increase the lifetime of the reactor to because the emissions are amortized, and bringing them to over 10 years will have a good contribution to the GHG emission of the ethylene produced. We also look at the efficiency, the conversion efficiency from sun to fuel, and we can see that below 3 or 4% around here, the GHG emissions are super high. They go to 100 or 200 kilograms of CO2 per kilogram of ethylene, and they decrease up to 25 grams of CO2 per kilogram of ethylene. So that's one parameter variation at a time, and that's why we still have this residual 25 grams of CO2, and this comes from, again, the energy for the production. because when we make the assumption that we use zero energy for the production, which is not the case, but here we can reach some good emissions for the production of photocatalytic ethylene, reaching 0.5 and being better than the fossil one. So this is the main parameter today, is the reducing the energy for the production of the photovoltaic solar cell. We also look at the solar irradiation in kilowatt per meter square per year, and see that it has an increase. It has an impact on the GHG produced with this reactor. So to our initial questions, what are the environmental impact compared to fossil ethylene? So we saw that the photocatalytic ethylene has more impact than in all environmental categories, except for the CO2 emissions for the PC reactor, because we have a credit for the avoided emissions from capture. And again, that's normal because we compare TRL4 technologies with the well-established technology, which is the fossil ethylene production. So this is normal that we have more impact in all categories. And the whole challenge is to predict what will be the impacts when the technologies will be upscaled. And we also spotted the hotspots, where are the huge contributors in which stages, in which impact categories. So to this sensor, the palladium catalyst and perovskite materials are the main contributor with the energy for the production. And now to make what we call ex-ante analysis of the technology once it's mature. It's hard to assess at this point, so that's why we are still discussing with the partners on the assumptions we can make to predict the energy consumptions once the technology has been upscaled. And that's why we made some parameter sensitivity analysis and also a parameter model, so we can move this parameter easily and following the technologies development, which are pretty fast at this point. So thank you very much for listening to me. I will give the floor to Carlos Andrade for the economic assessment of the technologies.
Okay, hello Maxime. Thank you very much for the introduction. Now I'm going to share my screen. Okay, and I'm going to. Okay, so thank you very much, Maxime, for the introduction. My name is Carlos Andrade. I'm a researcher economist at IFP Energie Nouvelles, and I'm going to present you some of the economic analysis that we have performed for the SUN2CHEM project. So this presentation is going to be structured as follows. First, I'm going to talk about the methodology. Then I'm going to present the case study that will allow us to discuss about the upscaling of the production. Next, it will be followed by the presentation of the results, first for the PC case and then for the PEC. After I will do some sensitivity analysis for the results, and finally I'm going to conclude. So concerning the methodology, first I'm performing a complete economic assessment of the SUN2CHEM project. This means that I'm taking into account all the different expenses that are incurred during the construction and setup of the production factory, the different cost for the operating cost of the production site during all the lifetime of the project, that is going to be 20 years. So the costs that are incurred during the construction and setup of the reactors are called capex, and the operation expenditure are opex. With all these cost elements, it is possible to compute the total cost of the project and some financial indicators that will allow us to discuss about the economic feasibility of the SUN2CHEM project. So one thing to consider that in this project we take into account inflation and discount rate, an inflation of 2% and a discount rate of 10%. So the main questions that are going to be explored with this economic analysis is first, what are the main cost components from the PC and PC reactors production? Can the PC and PC production be economic viable? And what is the levelized cost of ethylene from PC and the PC production? So now I'm going to talk about the case study. So first, it is important to mention that in order to be able to compute the different financial indicators, we have to upscale the production from laboratory to industrial scale. Otherwise, it is not possible to compare to conventional ethylene production. So I'm taking into account the 5% efficiency as the maximum presented before, and also the reduction in 90% of energy consumption. Moreover, some other assumptions that I'm considering to this business case is that we are going to produce like 365 tons per year, which means that it's going to be around 1 ton per day. This means that we need to produce 127 kilograms of ethylene per hour. This will require around 50,000 meters squares, and also 24 tons of steel and around 150 square meters of glass. This production, compared to current production at the south of France, is around 0.1%. And if we compare the energy produced containing in ethylene per year, and if we would like to produce the same amount of energy as the ethylene produced in this study, it will be required around 15,000 meters square of solar panels. Moreover, the formula that I'm using to upscale a materials price from laboratory scale to industrial scales is this one presented in the slide, with a gamma being of 0.75. That this will reduce the laboratory price materials from to 90% at industrial scale. So okay, so now I'm going to present some of the results for the PC first. So first, to produce the 365 tons per year, we are going to need 1,250 kilograms of photocatalyst. In the SUN2CHEM project, there have been analyzed different pathways to produce different types of photocatalysts. And the two that have reached the best technical performance is the one based on palladium and the other one based in gold. And if we take into account the cost of the different components, the one based on gold it results in the cheapest one. Also, we can compute the cost, the capital required to build a reactor. This is around $100,000. So with these elements, we can compute the different capex. So the capex are also constituted by inside the battery limit cost, outside battery limit cost, which give us the total fixed cost, and finally the total capital requirement that for the case of the photocatalyst is going for the PC is going to be 2.2 million euros. Concerning the OPEX, we have the variable cost that are around 114,000 euros. and a fixed cost of 127,000 euros. So we consider a CO2 price in this case of 100 euros per ton, and we are going to perform some sensitivity analysis for this case. With these different cost elements, we can compute first the levelized cost of ethylene of 1.6, almost 1.6 euros per kilogram for the ethylene produced through the photocatalyst pathway. So if we sell all our production at this price, we are going to have some positive financial indicators, mainly a net present value of 0.8, internal rate of return of 15%, which is okay. But however, this ethylene price is much more expensive than the current conventional ethylene that is whose price is in average 1.20 euros. So to make the PC ethylene production competitive with current ethylene production, it will be required a CO2 trading system price of 240 euros per ton of CO2. So now we are going to analyze some of the results concerning the photoelectrocatalysis. So first, there are two methods to produce the photoanodes needed for the PEC. So, but the one resulting in the cheapest method is the electrodeposition one, and we can observe that is the FTO and the MSO, and also the energy that are the elements that cost the most, that are adding the most to the cost of the photoanode. Moreover, concerning the photocathode, there are also two methods that have been analyzed in the SUN2CHEM project, the silicon one and the organic one. So in this case, the organic one results in the cheapest option, having the Fa element being the most expensive element in this pathway. So with these cost elements, we can, and with some other elements for the construction of the reactor, we reach very, very high capital requirements, which give us a very, very, very high levelized cost of ethylene from the PC production, which is going to give us, of course, a negative financial indicator. So I am not presenting them. So now I'm going to give some sensitivity analysis to these results. In this case, I performed the sensitivity analysis for the levelized cost of ethylene. I changed first the efficiency, also the annual capacity production of the industrial site, the changes to the CO2 price, and also to solar irradiation. So we can see that in all cases, first augmenting the efficiency will have a huge impact in decreasing the cost of ethylene for the PC option. We can see that if we increase the efficiency to 8%, the solar to ethylene efficiency to 8%, the levelized cost of ethylene will be reduced in around 20%. So is very, very, very interesting to reach the research to increase the efficiency. Moreover, if we also increase the annual production capacity of the industrial site to 50,000 tons of ethylene per year, it will massively reduce the levelized cost of ethylene, reaching a similar cost than the reference market price for ethylene currently. And if we reach, but thereafter there is decreasing gains, and if we reach the the capacity production that actually is present in at the south of France, we can reach a levelized cost of ethylene of around 1.1 euros. Concerning the change in CO2 prices, if we double the price of CO2, the levelized cost is going to increase in around almost 20%, and it has a similar impact when we reduce it. So it will reduce the levelized cost of ethylene in 20% if we reduce by 50% the cost of CO2 price. And finally, increasing solar irradiation, like changing to a country where there is more solar irradiation per meter square, is also going to have some benefits in reducing the levelized cost of ethylene. So some key messages. First, we have performed the economic analysis for the PC and PEC pathways analyzed in the SUN2CHEM project. We observed that these two pathways are more expensive than the conventional electric production. We observe also that there are different strategies that could further reduce the levelized cost of ethylene from the PC and PEC reduction, and mainly for the PC production. We can see that there might be potential pathways that can place the PC ethylene production in a green ethylene market. So thank you very much for your attention. We continue the presentation with Hugo.
Thank you, Carlos. I think my presentation is loading right now. Once you confirm that you can see it, I can start.
Good.
Yeah.
You see them?
Yes.
Okay, perfect. All right. Well, my name is Hugo GRASSET. This is the wrong. Sorry, wait. I'm on the wrong slide presentation, I think. Please include my notes. Sorry, I'm going to just do that again. Why am I not going to the page? There's screen. Okay. Now you should see it now, right? I believe. Okay. Thank you. Sorry about that. My name's Hugo GRASSET. I work for SOLINTEL. So it's a small, it's a SME just outside of Madrid in Alcobendas. We mainly have three areas of expertise. We have sort of engineering services that are dedicated towards the building, energy, and materials value chain. We have also an investment arm that actually buys and renovates buildings. And then we also have a small team that works on R&D projects at the national and also European level. As far as our activities in SUN2CHEM, we were mainly dedicated towards the sort of providing insights on exploitation perspectives and potential market uses down the line for SUN2CHEM. So that involves obviously some market analysis and insights. At this stage, obviously being a moderate level to low TRL level project, there's still a lot of uncertainties, obviously, and as you have probably seen with the two past presentations around the results. So it's obviously more a question of seeing or of discussing how or under what conditions TRL improvements should continue rather than actually talking about full-on or full-fledged take-to-market strategies, so to speak. As far as presentation, I always kind of like to start, before getting to the actual core, the meat of the presentation, I always like to start by the general outcomes or conclusions of the study. And essentially for SUN2CHEM, what we have is a promising set of market applications for the solutions, which could greatly benefit the competitiveness of the European industrial ecosystem. But as has been made evident just before with the past studies provided by IFP Energie Nouvelles, there's still many improvements needed in order to reach economic viability of the solutions. As far as this presentation, we will, in order to see kind of the future market potential or maybe exploitation strategies that can be applied for the project, will be essentially the presentation will structure itself around first a presentation of the methodology that we use during the project, so our innovation management process, the state of the solar fuels market and the state of the ethylene market, which are basically kind of go hand in hand, but these are the domains of applications for the SUN2CHEM results down the line, obviously. And then from a sort of overview of the state of those markets, how or what insights we can get out of this in terms of future applications and strategies for SUN2CHEM results. So as far as the innovation management process, it's a pretty standardized process. Essentially, we have three main building blocks, one of them which is a preliminary identification of innovation potential with basically just over varying kind of regional trends and market trends in our markets of interest, which in this case obviously are the solar fuels and mainly actually the ethylene markets, as we'll see later. Quantifying total market value, and then we also obviously try to sort of contextualize the past economic studies and life cycle cost studies with certain price dynamics and trends within the market to actually know how far off we are from an economic viability and competitive standpoint from the market. And then obviously from that take some conclusions from the exploitation strategy. So starting as far as the actual solar fuels market goes, so obviously we actually didn't focus too much into the all of the use cases for the solar fuels markets. We generally basically separate them into direct approaches and indirect approaches. Indirect approaches including thermochemical processes and most notably PV plus electrolyzer approaches, which isn't always the case, but we included them here. But that's actually a key element since that basically involves sort of renewable hydrogen, which is basically receive most of the attention in the solar fuels market at this stage, especially from the point of view of storage of renewable energy as fuel in terms of main use cases. And this is basically made clear by the actual state of the industry from a technology readiness level perspective when it's actually we'll say categorized into the three main sort of product areas, which is sustainable hydrogen, sustainable ammonia, and then chemicals and fuels. We basically see that obviously hydrogen is at a much more advanced state. We are looking for our processor technology. We're looking by 2030 at TRL levels that could ideally reach around TRL level 6 to 7 if research continues in this direction. And then obviously here you can see that in terms of advanced electrolysis, hydrogen, of course, receives most of the attention in the market. TRL levels are already at 9 for alkaline water electrolysis and then proton exchange membrane electrolysis. So what does that mean? Well, essentially from a sort of a traditional solar fuels perspective, which is sort of traditionally in this market focused on use cases that are more geared towards renewable energy storage, and then also, of course, application for transport, buildings and the like. All the attention is basically mainly given to green hydrogen, as you can see here as well with the capacity additions of the recent years. And what does that mean in terms of SUN2CHEM market? Well, it means that most of our actual analysis was brought towards essentially we applied most of our focus, or we think that most of the potential for the solutions down the line is for the production of fossil-free based chemicals for industry. As far as the industry in question for that, obviously is the all industries using ethylene and basically ethylene markets at whole. Moving on to actually the core of the analysis that we have performed, which is on the state of the ethylene markets, given that we believe that the applications here will be geared towards production of ethylene as a feedstock towards other industries. We have basically focused on identifying main regional trends with regional production and consumption figures, capacity players, and cracker feedstock costs and margins in order to provide more deeper insights in terms of price and macroeconomic dynamics behind this market and how SUN2CHEM compares to that point of view, or where it can come in and how far off we are. Industrial applications and market segments, and then competitiveness of the actual market in terms of new entrants to know what it would mean for SUN2CHEM to actually become a player within the English market, or not SUN2CHEM, but obviously a player taking the results from the project, taking in the market. Just to go over the main data in the beginning, essentially from a market volume point of view, nameplate capacity right now in Europe sort of oscillates between 22 to 24,000 kilotons per year of ethylene. And that's with crackers operating at around 80 to 90% nameplate capacity. So that if you actually look at the production figures in 2021, and then take average monthly contracts or monthly future contracts and spot rates, we're looking at about $21 billion in value. So the actual key players that were integrated within the analysis for the general sale markets are listed here. So there's the actual European capacity on the right side with the crackers that we were able to sort of gather within our data, and that's for 2019 production year. These are the actual national production rates. You can actually see that in most countries, there's actually representation in most European countries, although quite surprisingly, probably for some, production is actually higher in terms of well, actually production volume is higher in terms of in Western Europe compared to Eastern Europe. However, the year-on-year production rates are going up at a much more higher rate in other nations. In terms of this is actually when it gets a little bit more interesting in terms of the market dynamics, and it's basically trying to look at cracker feedstocks and then dynamics in terms of cost margins and price setting within the ethylene markets, so that we can start benchmarking it against the performance of SUN2CHEM products. So as far as when actually getting into the price dynamics to obtain a deeper insight in the market, what we have is that essentially crackers in Europe are essentially working on naphtha. This is because Europe essentially has a steam cracker infrastructure which is aging. There are some more recent sort of crackers like Project One by Ineos who work on ethane, so changing the feedstock, although this hasn't come without a fair share of social acceptance issues and legal challenges, actually. But this is actually an important insight given essentially the one of the major issues affecting the competitiveness of the ethylene market in Europe right now, and the chemical industry as a whole, is actually the energy intensive nature in the exposure to naphtha prices, and in turn also the fact that it's all dictated by crude oil. When you actually obviously plot or the time series in a chart, you can see that ethylene prices and oil prices have in some studies actually above 95% correlation, 78. Although we know essentially on a 2018 to 2023 sort of time frame, we've been earning 85% correlation rates, which is obviously not very surprising. When we join all this information together, we can see that through the lens of the European ethylene market, basically energy costs are the Achilles heel of European industry in general. Cost differential, for instance, here, due to the fact, obviously, that Europe is relying on some feedstock that is a lot more expensive. The sort of cost differentials that you can see are about twofold, actually, compared to the US, for instance, or Middle Eastern regions, which obviously inevitably has an impact on cracker margins in Europe, which are, at the moment, we calculated them at about 400 to 600, which is an estimate in line more or less with S&P Global, S&P Global's reports on cracker margins. This obviously has inevitable impacts also on the competitiveness of the rest of the European industry at whole. So what does this mean? Well, obviously it demonstrates a clear market case for solutions capable of improving cost competitiveness of the solutions and limiting our reliance on fossil fuels, at least on a long-term horizon, obviously, because this is not for tomorrow. But the benefits coming from that will not just affect the sort of sector, but other industrial sectors at large. In terms of the actual, so this is mainly just the market segments to which ethylene is applied. The idea here is mainly just to get an idea that ethylene in terms of demand will more or less be stable throughout the coming decades as well. So it's not, you know, we can't look the other way either, thinking that demand will generally reduce, as generally it is rather stable, although moderately coupled with GDP. So solutions do need to be found to decarbonize also these production of organic bulk organic chemicals. And so as far as actually getting into the competitiveness of the sector, one of the things that we've done is, in order to understand essentially the market environment from a competitiveness point of view, we performed a 5 forces analysis, which of the actual ethylene market in Europe to understand the ease of entering as a new market player, and also provide insight in terms of the best market strategy for SUN2CHEM solutions down the line and how they should position themselves. So yeah, this is obviously still sort of looking very far down the line given the TRL levels of the project, but it also is capable of giving an idea and insights, at least in terms of how to position the next or how to use demonstrators for next TRL improvements and the like. So as far as the actual market goes, just to go over some main dynamics, in terms of rivalry amongst existing competitors, we have a market that's obviously very mature with large established players, which brings the level of competitiveness up, especially when you take into consideration that the barriers to exit are huge, given plant investments. Threat of new entrants are immense. There are immense capital requirements for new entrants, which basically takes the threat down considerably, which isn't necessarily a good thing for SUN2CHEM. Essentially, even from an economy of scale point of view as well, a 1.5 million ton per year ethylene plant now is very common within the European landscape. So it's obviously involves the initial capital requirements, and then your ability to function at scale. And then also, since we're talking about like long-term future contracts, generally switching costs and access to distribution channels can be a little bit limited, at least at the beginning. As far as threat substitute products, we related most of the study. Obviously, in our deliverables, you can find more extensive coverage of this, but basically we limited the study towards the actual alternatives in producing ethylene within the market, which obviously the problem at this stage we know is all the many new developments are very low TRLs, which means absolutely not scalable or not cost competitive. So threat of new substitute products at this stage is pretty low. And in terms of bargaining power of buyers, we have moderate price sensitivity in the market. Ethylene remains a critical input to many large-scale industrial processes that will inevitably lead to some level of price elasticity. And then switching costs, well, once again, we're looking at future purchase contracts that may complicate swiftness for switching in what are often long-term industrial contracts. And then recently, there's actually the issue of overcapacity in the market in the recent years that might complicate things as well. In terms of the bargaining power of suppliers, which is our last sort of element or force, we have a relatively large number of very large to large naphtha suppliers, which should increase the ethical bargaining power. Decrease the bargaining power of suppliers. Inputs are undifferentiated as well. So of course that also should decrease their power. However, it is obviously substituting from one feedstock to another is cash intensive. And then there's so many suppliers that are vertically integrated, obviously. So that's obviously it goes actually adds some bargaining power for the suppliers. So what does this mean? This is probably the most interesting part. What does all of this actually mean for SUN2CHEM? What basically making sense of this information? What does it mean in terms of positioning SUN2CHEM results in the market? Well, we've kind of formed just as an overview of the main dynamics, which were some inputs from partners within the consortium, and then also some work of our own. We basically sort of created the SWOT, which summarizes some of the main points. But what we actually want to mainly focus on here is obviously the weaknesses, which are the overbearing or the elephant in the room, we'll say at this level, at this moment. And I think that it was quite clearly demonstrated by Maxime and Carlos just before. It is the essentially we are at low TRLs, which makes the technology right now quite difficult to scale and very costly. And then we'll see down in this analysis, but also from what we were seeing earlier on in our data sets, fossil fuels are still more cost competitive, providing low incentives in actually adopting novel large-scale energy technology. So, I mean, from obviously all this is due in part for the low TRLs. I'm going to go over this, but essentially our PC and PC reactors are at the TRL level 4 right now, so moderate TRL level. In terms of actually competing or positioning it in the market, at this stage in time, when you actually look at pricing dynamics within the ethylene market, and Carlos was mentioning this before as well, with the price of conventional ethylene, seems highly unlikely that ethylene reaches threshold break-even price levels or price levels that would imply break-even levels for some of the project results at this stage, at least in the life cycle cost analysis that was provided, and at least organically outside of an unexpected supply shock. So, you know, for instance, when you actually look at the scatter plots and do linear, you know, through simple linear regression work, you generally, even through consolidated forecasts by EA, you never actually get to a dollar or a Brent spot rate that will lead to an actual price of interest for or a sustainable ethylene price for the SUN2CHEM project. So there's definitely a cost issue at this stage, at least for large scale production. And then obviously, the current, as I was saying, the current IEA forecasts Brent spots of $100 per barrel. Although this obviously changes all the time. As far as regulation that could help you, well, currently the allowances scheme the allowances right now since 2024 are trading at about 80, 60 euros tons of CO2, which also does not provide a sufficient sort of price correction mechanism for making the solutions viable economically. And then there's actually, on top of that, within the EU ETS system, there's the fact that actually there's free allowances that are being distributed towards industrial players. Benchmark value, which was the phase 4 allowances essentially, and free allowances is fixed for steam crackers at a level of 0.681 tons of CO2 equivalent per ton for the benchmark 42, which is steam cracking, which basically implies 22 million tons of CO2 equivalent a year. So that bulk almost, if you go back to our capacity figures earlier on, that actually covers a pretty important part of the steam of the ethylene market in and as of itself. And so right now there's definitely insufficient price mechanisms which will actually adjust the market price to make SUN2CHEM competitive at this stage. So what does this mean in terms of the actual exploitation roadmap? Well, during our actual exploitation seminars with the project partners and discussing around this, that it basically limits, when we look at the target use model and how we need to further develop the solution down the line, it basically limits the economic applicability of the solutions in industrial and operational environments, at least for TRL 6 and 7 scaling, and at least within its current configuration. And so generally the common sort of idea that the partners SUN2CHEM project were having during especially the Horizon Results Booster seminars was the fact that essentially in TRL 6 and TRL 7, minimum viable products could be viable, basically having scaled down minimum viable products applied in decentralized production facilities that need less amounts of ethylene, and that maybe don't rely on the traditional supplier network and are potentially in areas with less coverage. Those could be the pilots of interest for scaling up to TRL 6 or TRL 7. And basically the advantage of these minimum viable products and having low scale products is obviously that they offer viable strategies for lowering the costs and then also mitigating the future risks in terms of larger scale implementations and identifying the problems and then scaling up. What could these be? We've essentially focused most of the main idea has been around potentially climacteric fruit ripening facilities or facility providers, and then also ethylene oxide sterilization for projects and providers. So that is sort of down the line as far as taking the project from TRL or from the current TRLs to potentially a TRL 6, TRL 7. We're thinking that probably the best approach is mainly these kinds of small scale decentralized approaches rather than looking at we'll say a traditional supplier, chemical supplier business model, if you like. As far as just looking at some of the other elements of the exploitation roadmap, right now, obviously, we've been relying, or the SUN2CHEM has relied on EU project grants, and then some of the last background was national or university grants, so a lot of public grants, basically. There's also right now a lot of partnerships going on with larger chemical producers, the ones actually mentioned earlier on, through partial acquisitions, mergers, or investment technologies, which might be of interest to the project. And as far as the revenue models, given what we were saying in terms of the potential decentralized approaches, which represent the highest potential for the project at this stage, the revenue models here are basically different to your conventional model of selling chemicals or selling a bulk product. Given that the approach would basically be the actual installation of larger scale devices for niche decentralized applications. And so you would actually have to find a pricing model which takes into consideration the payback the potential savings and payback periods for the actual buyers or companies that are implementing these solutions. And that obviously implies taking a good look at the state of the ethylene market and mainly price dynamics and EU ETS price evolutions, given that the actual allowances that the ethylene industry has at this stage are going to reduce, obviously, down the line. As far as basically, this is just sort of additional comments in terms of the insights for the future of the exploitation. But in terms of the actual risk assessments and priority mapping that was done by the partners of the projects, the consortium is, of course, well aware of the cost related issues. It's exemplified here in the actual risk assessment and priority mapping that they've done. Highest risk grades are all given to, or all, they basically pertain to cost drivers mainly. So it's something that the consortium at large was very well aware of. And as far as taking conclusions from this, well, as far as future discussions in terms of whether to continue research, whether to actually scale to TRL6 and go down say the milestones that were exposed in our exploitation roadmap, it'll be important in future discussions to actually talk about the main cost drivers and hotspots, and talk about obviously how addressable they are through further research and developments. For instance, Carlos, in his sensitivity analysis, was demonstrating how essentially that's taking the solid ethylene efficiency rate up to 8%, you're starting to look at basically costs of ethylene that are more normalized within market levels. How possible is that within the near future, or what kind of time horizons, and under what kind of funding? Those are the questions that remain for the consortium this stage. And that's about it on my side. So thank you very much, and yeah, I think that's it.